Hello friends, welcome to my channel. In this video we are going to discuss about how the mux can act like a universal logic gate, or we can say how the mux can act like a universal logic converter. That is what we discussed in our last class, like one important point. And also we observed that in our last class 4 by 1 mux operation and 8 by 1 mux operation. Now let us discuss this point. Now here it is the 2 by 1 mux we are considering. With the help of a simple 2 by 1 mux, now we are going to design all these like basic gates and universal gates and special gates also. Now let us see how. So just take this 2 by 1 mux. So 2 by 1 mux, it is having two inputs, one selection line and one output. This is the simple 2 by 1 mux, and this is the output equation, we know that. So here one selection line means the selection line value, it may be a 0 or 1. Based on that you may observe the output equation here, like a S bar and a S. Now the same, now I am represented with in place of S I am represented with A. The simple reason is so to further like to design further logic gates, it is easy for us. So in place of S, now I am replaced with A. So now this is the required equation, output equation for the 2 by 1 mux. So now I am going to design a buffer. We know that buffer means whatever it may be the input we are giving, that is what the output. Now how it is getting, just observe that. Now whatever it may be the inputs I0 and I1 values, based on the I0 and I1 values, now we are going to get the different logic gates here as an output. Now if input is 0 and 1, I0 value is 0, I1 value is 1, so that means now we are applied here. Now A is the selection line, so according to the equation, A bar into I0 plus A into I1. Now substitute the values of I0 and I1 values here. This will become y equal to A. So A is the input, output is also A. So hence it is satisfied, it is act like a buffer. Now we are designed with the help of 2 by 1 mux. Now second one, design of NOT gate using 2 by 1 mux. This one also observe here. Previously we are giving 0 and 1 are the inputs. Now 1 and 0 are the my inputs. Like I0 value is 1, I1 value is 0. That's it. Substitute the values here, the same equation. Here you will get y equal to A bar. That means we know that the NOT gate operation, if A is the input, output is A bar. That is what we are getting. Hence this mux can also act like a NOT gate. Next we are going to see AND gate. How the mux, this 2 by 1 mux can act like a AND gate. So here now, so I told you already, based on the I0 and I1 values, different values we are giving. Based on that, according to that we are getting the required output. So now I am giving 0, I0 value is 0 and I1 value is B. That's it. Substitute in our equation, standard equation, 2 by 1 mux standard equation. So A bar into I0 plus A into I1. What is I0? 0. What is I1? B. So 0 into anything, it is 0, A into B. So that is what we are getting. So hence it is satisfied. AND gate also. Now with the help of 2 by 1 mux, we can easily implement AND gate also, based on the inputs are 0 and B. Now, so now it is easy to understand next NAND gate, because we know that AND gate and NAND gate both are complement each other. Just whatever maybe the inputs I am applied here, just a complement inputs I am applying here for designing of NAND gate. Like 0 and B are the inputs previous case, now 1 and B bar are the my inputs. Now substitute here, substitute in our equation. So this will become like this, like A bar into 1 plus A into B bar. Now apply some, this is nothing but boolean expression, reducing the boolean expressions, like we already discussed with this one. So a bar plus a into b bar, like here we need to apply the distributive law, a plus bc, which it is equal to a plus b into a plus c. Now like that, a bar plus a into a bar plus b, anyway a bar plus a it is 1 only, we know this property also, that is a bar plus a which is equals to 1 only. So that is 1 into a bar plus b bar, so this will become a bar plus b bar. From De Morgan theorem, a bar plus b bar which is nothing but ab whole bar, that's it. Hence based on these inputs we can also design NAND gate also. Now the point is here, one note point here you need to observe, that is directly we cannot give b bar as an input for I1. So we can give 1 or we can give 0 or we can give b like that, but b bar it is already complementary input. How we can get b bar? With the help of simple NAND NOT gate, right? With the help of NOT gate. So we can, just now we observed that NOT gate also we can implement with the help of 2 by 1 mux. That is the reason. So this is the another way to represent. Now observe here, this is the another way to design the here two by 1 mux are used, right? So this first 2 by 1 mux, it is act like a NOT gate. This is act like a NOT gate, this one, and this is given as a b bar as an input, one input, and I0 input is 1 itself. So this we will get a into b bar. That is what just now we observed here. Hope you understand. So both are same. You can follow this one. It is correct only. Next. So but you need to remember the note point here. So next, design of OR gate. So to design OR gate, here I am considering b and 1 are the inputs. I0 is given to b, I1 is given to 1. Now observe here, we know that OR gate output right here somewhere here, so that you can verify later, y equals to a plus b, it is what our output. Whether it is we are getting or not, just check here, substitute in the formula, then do the some apply some formula like theorems and reduce the expression a bar into b plus a. So apply distributive property, so this will become a plus a bar into a plus b. So finally a plus into a plus a bar which is equals to 1. So finally a plus b. So hence with the help of 2 by 1 we can also design OR gate also. Next, NOR gate. Observe this NOR gate. So NOR gate, just complementary inputs I am taken here. Sorry. The complements inputs I am taken here. Just wait. So right. So this is our NOR gate. Like b bar and 0 are the my inputs. So apply the formula and substitute those values. You will get easily a bar into b bar. That is from the De Morgan theorem. We know that it is a plus b whole bar itself. So that is the reason. So it is easy compared to OR gate. NOR gate design, it is very easy here. So with the help of 2 by 1 mux we can design NOR gate also. Next, last two, observe the special gates also, XOR and XNOR gate. So first observe this XOR gate using 2 by 1 mux. So one input is b, I0 is b. Observe here, I1 is I am giving b bar, and my selection line is always same, a, for all these gates. my selection line input is always A, and my inputs I am changing, like somewhere sometime I am 0 and 1 and 0 and B, or 1 and B bar, like that. So you can observe what is going on here. So for the XOR gate, if I want to design, I0 I am giving B and I1 I am giving B bar. Now substitute formula and you can easily get this one. Okay, so I0 value it is B, I1 value it is B bar. So A bar into B plus A into B bar, which is nothing but A exclusive or B direct formula. Now NOR gate also, it is B bar and B 2 by 1 mux, A bar into I0 plus A into I1. Directly you will get Y equal to A exclusive NOR B. And after that, the above logic gates we can also implement with the 4 by 1 mux also. It is very interesting. We can also implement with the 4 by 1 mux also, but we require the truth table. But we require the truth tables of logic gates. So what are the truth tables? I think we know. We are very much familiar with the truth tables of our basic gates and universal gates. Like what is the AND gate truth table? So if A and B are the two inputs 0 0 0 1 1 0 1 1 4 combinations, two inputs 4 combinations, AND gate output is 0 0 0 1. We know that OR gate output is 0 1 1 1. NAND gate is completely complement of AND gate, that is 1 1 1 0. This is the NOR gate, complement of OR gate, that is nothing but NOR gate 1 0 0 0, and XOR gate 0 1 1 0, and XNOR gate complement of this one 1 0 0 1. Now we know very well 4 by 1 mux operation. So for 4 by 1 operation, two selection lines will be there. That selection lines I am considering A and B. In our previous video, I think we are taken S1 and S0. Now we are taking A and B in place of S1 and S0. Both are same. So now if you want to design AND gate, just I0, I1 and I2, I3 inputs are, just take these 0 0 1 and substitute here. You will get the Y equal to AB. That means whatever it may be, the according to the truth table outputs. So these values, if you supplied to mux, you can get the AND gate operation, right? Like similarly, so like that we can easily implement with 4 by 1 mux also. Not only 2 by 1, we can also implement all the basic gates and universal gates and special gates. We can also implement with 4 by 1 mux also. So this is just simply AND gate. Next, similarly OR gate also you can observe here, that is also there. So OR gate, the truth table 0 1 1 1. So apply that 0 1 1 1 here. Right now you can see, substitute here, and so this the I0 value it is 0, I1 I2 I3 values are 1. So now we need to solve the this boolean expression. You can solve this method or you may solve this method also, both are same, right? So I mentioned both the methods here. So here you will get A plus B. Next XNOR gate. So here XNOR gate truth table, XNOR gate 1 0 0 1, last one XNOR gate, right? So you can observe here that XNOR gate output, one second, right? Four by 1 mux XNOR gate. So 1 0 0 1. So substitute here and just substitute in our formula, then you will get, anyway these two are 0 and I0 value is 1, I3 value is 1. So again it is direct formula. It is very much simple compared to this OR operation. or so. Next, if you want to design NAND gate, see here, we know that the NAND gate truth table, that is 1110, that 1110 you can apply it here and you will get the output, NAND gate output. That's it. Hope you understand this one. uh, if you I hope you understand all these concepts, like the design of basic gates and universal logic gates. If it is useful, so please like, share and subscribe my channel, and please give me your valuable suggestions